somebody like to come up and, or from your seat, tell me how you figured out the answer to letter A? Nigel, go ahead.
Well, I saw that the water changing the concentration of H2O has no effect on the initial rate of change.
Mm-hmm.
So I made that the zero order.
Mm-hmm.
And then changing the concentration of the other one
Mm-hmm.
had a one-to-one effect. So when that was doubled, the rate of change was doubled. So I gave that first order.
Yep. Good. Yeah, so this is typical table you're going to see for questions like this. 3 experiments. You've got to compare the ones, yes, that's right. You got to compare the ones where only one thing is changing at a time. So for the water, again, we're comparing experiment 1, experiment 2. We're looking at the rate. There's no effect on the rate. And then for the other substance, the 2-methyl-2-bromopropane, I think is what it is. You'll learn about that later. Multiplying it by 2 also multiplies the rate by 2, so that gives us a doubling and doubling. The same thing is happening, so that's a first order reaction. If it was doubling and quadrupling, it would be a second order. So, all right, so how would you then write a rate equation for this if that was the case? Somebody besides Nigel. So we know the orders of reaction, right? We know that we write the rate equation like this. Rate is equal to a rate constant times the concentration of each reactant raised to the power of the order of reaction for that reactant, right? So we can plug in what we know to this baseline equation, right? Oops. So how would you write the rate equation? All right, Nigel, why don't you let us know?
It would be K times the CH3CBr1 to the first.
Mm-hmm.
And then the other one is to the zeroth, so you would have to include it all.
Right. So that you can write the one there, or it can be in one of chemistry's many invisible ones, right? Anything to the first power is that thing. Anything to the 0th power is the number 1. So it would be this times 1. And again, we don't tend to write the 1. So this would be the most basic way to write the rate expression for this reaction. Okay. Now that we have a rate equation, we figured out the exponents, and we figured out that we don't even have to include the water at all. Now we can solve for K, right? So you're going to pick an experiment, if you haven't done this already. Now that you have an equation, you're going to pick one of the experiments, and you're going to use the data in that row to solve for K. So you've got concentration here, you've got rate here, solve for K. So go ahead and do that right now if you haven't already done that. If you need to rearrange the equation to get K by itself, it'll be the rate over the concentration. In this case, because that's all we have. So can you do letter C then? So I'm asking you to do letter C. Yeah. What do you mean?
You said it was K rate over the
Uh-huh.
but
It's going to be the concentration of the 2-methyl. Yeah.
oh, okay.
Right. So each experiment has a concentration. This is a great question. So we've just asked which concentration. Well, each experiment has concentration and rate. Okay. It doesn't matter which one you pick. You can pick any of those three, and you should get the same answer, because that's how the rate constant works. Okay. And actually, let's try that. Let's have somebody do experiment 3. Use experiment 3. Who has not started yet and wants to do experiment 3? Nigel, did you use 1 or 2? Okay, then can you do it again with 3? We'll see if we get the same answer. Thanks. Yes. Mm-hmm.
So for the rate,
It's
it's okay. So I was accidentally doing it backwards.
okay, gotcha. Mm-hmm. Oh, I see. You changed that into a decimal for both of them. Okay. But somehow didn't end up with the correct answer. So you should have gotten, if you did it in floating decimal, or you can convert it to scientific, or maybe your calculator gave it to you in scientific. Okay. 4 times 10 to the negative 6th, or negative 5th. So, and it shouldn't matter whether you do 4.0 times 10 to the negative 6 divided by 1 times 10 to the negative 1, or 2.0 times 10 to the negative 6 divided by 5 times 10 to the negative 2nd. Okay. Let me do a quick reminder of the calculator buttons for scientific notation, because I know some of you will be using these calculators on the exam eventually. You're always welcome to use your own, but always make sure that you know how. So what is it, TI 84? Is it 84? Oh, TI 30X. TI 30X. 2S. There we go. So let's just get a picture of that so I can show it to you a little bit better. Okay. Image. Oh, I don't know if that's going to come out. No, let's do a different one. All right, we'll just go with new tab. Is it a little bit bigger? Nope, that's as big as it gets. Okay, well, maybe this will, if I do it this way, it'll come across a little bit better on the screen when I blow it up, or maybe not. Okay, not really, but we'll deal with it. I know I have a slide somewhere with this in better condition, but for scientific notation, say you want to write what is it, 2.0 times 10 to the negative 6th. There are multiple ways to do it, but yes?
On the last slide, would it be per second or per minute?
Oh, you're right. It would be per minute. Thank you. Good catch. Good catch. And we'll talk about that actually in a little bit. But I want to go through the. Yeah. So we know that it's per minute because the units of the rate are moles per decimeter cubed per minute, and the rate for the units for concentration are moles per decimeter cubed. So these two cancel each other out, and we end up with this on top as our unit. We're going to talk later about the pattern of units for K under different situations. Also, I just want to mention that B, I forgot, was also asking for the overall order of the reaction. What is the overall order for this reaction? So the overall order is going to be the sum of the orders for all the reactants. So we've got 1 and we've got 0. So it's first order with respect to that reactant. It's also first order overall because that's the only term in that rate equation. Okay. And so we'll talk about when you have a 0 first or second order reaction, what the units of K should be. But we'll get to that a little bit later. All right, so say I want to type in 2.0 times 10 to the negative 6. There are a number of ways you can do it. The fastest way is to do 2, and then second, and then this button here, which you can't really see, but the shifted thing says EE, okay? And that means 10 to the, times 10 to the. That's what the EE means. Some calculators have it just as E, like a capital E. It's not lowercase e because that's different. That's the inverse of the natural log, right? So we want to take or you could do this 2.0 if it's more than, the 0.0 doesn't matter on the calculator, but second EE, and then you want the negative sign, okay? before the number. If you don't put the negative sign before the number, it messes it up. Okay. If it's a positive number, you don't need this, right? But you've got to use that in order to get there. And then you can treat it just like any other number. And so I can say this divided by, what is it? 5.0 times 10 to the negative 2, 5 second EE negative 2, okay? And that equals, all right? Now, if my calculator is set on floating decimal point, then what that's going to come out as is going to be the decimal notation. So it will come out as 0.00004, okay? If it doesn't come out that way, if it comes out as the scientific notation and you want to put it in decimal notation, the way you switch back and forth is second psi eng, and then use the arrow button to toggle. So you're going to go second, and then this button goes between floating scientific and I forget what the flow, psi, or eng. I actually don't even remember what the engineering version does. It's some. I could probably dig it up if I thought about it long enough, but I never use it. I just go between flow, which is our regular, what you think of as regular decimal notation, meaning that the decimal place is wherever it is. Okay, and remember in scientific notation, the decimal place is always after the first non-zero digit. So that's why it's different from floating decimal. So when you see flow, that means regular. When you see psi, then it means scientific. And it'll actually show up on the screen. You'll get a little psi here if you have scientific notation on the calculator. So if you see that and you don't want scientific notation, you just go second psi, and then you use the arrow keys to go back to flow. Okay. All right. Again, your mileage may vary with different calculators. These are the ones that we have here and that we will give out for testing if you don't have your own. So might as well learn how to use them. Okay. Okay. So you will have to do this. Chances are pretty good that you will see something like this on a test, on your exam. They're 100% that you're going to see it on a quiz here in this class, okay? There is exercise 2, which I will leave you to do on your own. And the answer key to this whole packet is already posted in Canvas, so you can check your own answer. I want to go a little bit further today to talk about these different orders of reaction and what it would look like in a graph. So this is something that you can do if you are doing, say, an IA experiment, and you want to know the order of reaction, overall order of reaction, for the reaction that you're studying. Okay. One way you can do this is by just looking at either your concentration over time graph, which is what you're usually collecting the raw data of, or you can look at the rate versus concentration graph by taking these data, taking the slope, and making that the y-axis, the slope of this line, and then the x-axis is concentration. Okay, and so if you have a zero-order reaction, you're going to end up with, now this is looking at the concentration of the reactants, obviously, because we're going from a high concentration to a low concentration. It would be the opposite if we were talking about the products, right? So if you're measuring product rather than measuring reactant with whatever your technique is that you used to study your reaction, then it might be like this if we're looking at products. either way, the rate is constant, right? If the rate is constant, no matter what the concentration is, then the rate versus concentration graph is going to be a flat line. And that means that the concentration doesn't matter, okay? So if we're talking about the order of reaction with respect to the water in the last example, it would look like this. If we change the concentration of water, we would not see an effect on the kinetics, okay? And if we graph it like this, it would just be a flat line. If we talk about a first order reaction, okay, now our concentration versus time graph is going to be curved, okay? The graph is curved because the effect of the concentration on the rate is changing as we go along, okay? So as the reaction progresses, the concentration gets lower, and that also lowers the rate, okay? So that's why we have that curved line, and again, it would be, you know, something like this for product. Well, that's a terrible line. Something like that if you're measuring products, right? So if you have a graph of these data for your experiment and you see that it's curved like this, you can say this is probably a first order reaction. And if you then graph rate versus concentration and you see that direct relationship, that one-to-one direct relationship, then you confirm that yes, this is a first order reaction with respect to the concentration that I'm changing. Okay, the substance that I'm changing the concentration of. So you can do it mathematically, but you can also do it graphically. Okay? Obviously, to get good graph data, you need to have a lot of points. So if you only have two different concentrations, you're not going to get as much information out of this. And then the reason why it's helpful to do the rate versus concentration graph for this is that you also get a curved line for concentration versus time for a second order reaction. The curve looks different, okay? It's sometimes hard to tell when you're working with your own variable experimental data if the curve that you see is this curve or this curve, right? So again, when you plot rate versus concentration, you will see a curve here for a second order, an exponential curve. Because if we double it, we're going to multiply it by 4. We're going to multiply the rate by 4. Okay. So this is what you would do, and I'm hoping that to next week have us play around a little bit with some of your experimental data from the lab that you did to show you how this would work in real life. Okay. You will also see stuff like this on paper 1A in the multiple choice. They'll give you 3 different graphs and say which of these shows, or 4 different graphs and say which of these shows first order kinetics. And you'll have to pay attention to the fact that some of the graphs are going to be concentration versus time, and some of them are going to be rate versus concentration. So you're going to have to, you know, figure out which is which and what it should look like. Okay. Okay. To circle this back around to the reaction mechanisms that we started talking about in this unit, okay, we can derive a rate equation based for non-elementary reactions based on what we theorize as our reaction mechanism. Okay, so the stuff that we're doing here, stuff that we're doing here as far as looking at the overall reaction is only really going to work if we have an elementary reaction. Okay, but we can look at this. We can look at rate equations in order to determine whether a reaction mechanism is possible. Okay, so this is one way that we can disprove a reaction mechanism, or at least give some more confirming evidence for it. Okay, so the whole point here is that you're not using the whole equation, you're using just the slow step. Okay, because that's the rate determining step, so that's going to be the step that goes into the rate equation. Because the fast step, it has nothing to do with the rate of the reaction, it's just going to go either right away or as soon as the slow reaction finishes. Okay, or the slow step. So if we're looking at this, we're just looking at the slow step, and we're also getting rid of anything that is an intermediate. Okay, because the concentration of the CL here, because the CL is an intermediate, is not going to be important. Okay, it's not going to have an effect because it's just going to get, or sorry, sorry, I'm doing this wrong. This was slow. I was looking at this as the fast one, but I think that's the next one. I apologize. It's Friday. It's been a long week. Sorry. So this one is, there's only one reactant, so that's the rate equation for that reactant. And so if this was an elementary reaction, we would say that the rate was going to be K times the concentration of this squared, because we have that 2 as a coefficient. Okay, so if we were saying this is elementary, we could write that rate equation based on the balanced equation, the coefficients of the balanced equation. But we're saying it's not, so instead we're going to write the rate equation based on the slow step of our proposed mechanism. Okay. So here's an example. This is actually going to be, this is where the intermediate comes into play here. So in this case, the second step is our rate limiting step, is the slow step. Okay. But we're not going to include the intermediate. Okay. However, in the rate equation, however, we have to account for the fact that this is part of the slow step. Okay. But where this comes from is from the reactants of the fast equation. Okay. So we're going to, in order to figure out the rate equation, we're going to take any non-intermediate part of our slow step and the reactants of our fast step, because that's going to determine how much of this we have. So we can't, because this is an intermediate, we can't change the concentration of this and figure out, what the order of reaction should be, or or do this experimentally, because we can't change the concentration of this directly because it's an intermediate that's only there for a moment. Okay, but we can change the concentration of these. Okay, so we basically put together everything that would influence the rate of step 2, which is the reactants, in this case, the reactants of step 1 and the non-intermediate reactant of step 2. So in this case, we are squaring the NO because it appears twice. Okay. So we're basically saying that we've got 2 NOs and 1 O2, and now we're using 2 as our exponent for the NO concentration and 1 for the exponent of the O2 concentration. Jacob J, did you have a question? I couldn't tell if that was a hand raise or not. Okay, great. Okay, yeah, so don't forget to include whatever reactants are in the slow step that are not intermediates or catalysts, right? Because you're also not going to include a catalyst in the rate equation. Okay. Okay. I think that is where I want to stop today. So when we come back next week, I'll probably do this as a warm-up, and then we'll get into some more stuff about K, the constant K, and how you can use this idea and experimental data to evaluate whether your proposed mechanism is correct or could be correct. Is it a possible mechanism? So we'll pull this back around.